glad to see all of you, or at least to see your names in front of black screens. I hope that you're not judging me too badly because Deanna has like a massive, cool whiteboard behind her, and I have a tiny one on a cheap easel behind me. I'm still trying. Today we have Connor Maloney giving his senior experience talk. Connor comes to us from the Madison area in Wisconsin. Connor's a biochemistry major, and last term I, and some others engaged in a medicinal chemistry tutorial that was largely based around student-directed work. And Connor put together some really nice talks about hepatitis C and its treatment. I encouraged him to beef that up. And I'm very impressed to see this talk and how much further he's able to do it. Again, I really enjoy how Lawrence can kind of make room for this sort of independent activity. And I think it's pretty cool. And there are lots of, I think, interesting societal, social justice type questions when it comes to the treatment of hepatitis that Connor is going to talk about today too. So without further ado, take it away.
Thank you, Stefan. All right, so hello everyone. My name is Connor Maloney, and welcome to my senior capstone presentation. So over the past couple of terms, I've become very interested in a disease called hepatitis C. And as with any disease, our ultimate goal to strive for is to cure individuals of that disease to prevent any unnecessary suffering that may come with it. And so I've been investigating the current state of treatment for hepatitis C using drugs called direct-acting antivirals, or DAAs, and the relevant chemistry and biochemistry that is necessary to achieve this ultimate goal. But before I get into any of that, I think it is important that we have a baseline understanding of what hepatitis C is. So hepatitis C is caused by a viral infection called HCV. This infection spreads through contaminated blood, and very simply put, what this virus does is it causes liver inflammation. There is both an acute and a chronic phase. The acute phase is considered to occur within the first 6 months after someone is exposed to the virus. And the only real reason why there's this distinction between the two forms is because for some people, this is just a very short-term illness. However, for most people who are exposed to the virus, the acute phase will progress into the chronic phase. So the virus is essentially able to take hold of the host effectively enough to become a lifelong infection. There are a long list of symptoms. There's fatigue, poor appetite, bruising easily, yellow discoloration of the skin, which is otherwise known as jaundice. However, a majority of people who are actually infected are asymptomatic, which to me, before a couple of months ago, seemed like kind of a strange phenomenon. And this is particularly scary because it means that many people can have chronic hepatitis C without even knowing it, all the while they are berated with chronic inflammation of the liver. And the figure you see in the bottom right are just modes of transmission broken down percentage-wise. As you can see, a majority of people get this disease or get the virus through the use of needles. It can be sexually transmitted, and actually before the medical community did proper screenings, it was sometimes transmitted via blood transfusions. So like I said, this acute phase, which will typically progress to the chronic phase of hepatitis C, and this is where the real damage occurs. After many years of chronic inflammation in the liver, there can be fibrosis, which is fibrotic growth in the liver, and this can cause damage. There can be cirrhosis, which is scarring of the liver, and something called hepatocellular carcinoma, and this is just a fancy medical term for a very common type of liver cancer that is caused by hepatitis C. And actually, fibrosis and cirrhosis can aid in the development of this liver cancer. Now, this progression varies quite a bit in individuals, but typically cancer will arise approximately 10 to 20 years after someone is infected. Globally, hepatitis C accounts for around a quarter of cirrhosis cases and a quarter of carcinoma cases. So this is a very impactful global epidemic. According to the CDC, over 71 million people in the world have it. And this is actually a pretty conservative estimate. I've seen estimates that are closer to around 170 million people. Now, being that it is asymptomatic, it is very difficult to lock down just how many people have it. It is not evenly distributed around the world. Approximately 1/3 of the disease burden is held in the Western Pacific region. So places like Australia, China, Cambodia, Vietnam, the Philippines, and so forth. And there is a high disease burden in low-income regions. And because of this, a majority of those who are infected lack the resources to get tested, or if they know that they have the disease, lack the resources to get proper treatment. And so there are actually 7 different genotypes that this virus has, and for each genotype, there are multiple subtypes that have been classified. So this is a pretty diverse virus in the sense that it has discovered many genetic profiles suited for survival and evolutionary fitness. Genotype 1 is most common in the US. Genotypes 1 and 2 have a diverse global distribution. Genotypes 1 and 3 account for 46% and 30% of global infections, respectively. And here I have a table just to give you an idea of how each genotype is distributed around the world. As you can see, 1 and 2 are found pretty much everywhere, and 3 through 7 are concentrated in particular parts of the world. So before I get to how these direct-acting antivirals work, I want to highlight some problems that face the treatment of hepatitis C using these DAAs, and some problems that still remain. And the first one is the effective treatment for all genotypes. A term that is frequently used in the literature is pan-genotypic efficacy. Now you know that there are 7 distinct genotypes. Well, this is very important because up until quite recently, patients' response to treatment would vary dramatically with genotype. So, for example, a patient with hepatitis C genotype 1 could be cured of the disease, while another patient with genotype 3, using the exact same treatment, would be completely unaffected, meaning the virus would survive. Another problem that still faces treatment is drug resistance. And it turns out that the biochemistry behind both of these problems is intimately related, which we will get to later on in the talk. Finally, another very important problem is the extremely high cost of these treatments using DAAs. And these are just some problems to keep in mind throughout the remainder of the presentation. And if you can think back, now we know that this disease disproportionately affects people in low-income regions. So high cost is going to be a very important barrier to entry that we need to mitigate. So HCV has different genotypes, making treatment difficult. So just to give you a little bit of background for this, much like our genetic code, the genetics of a virus encode for specific amino acids. And these amino acids are the building blocks for their proteins. These proteins are necessary to carry out various functions to keep the virus alive. And so with each new host, that is with each new person that the virus infects, comes a new environment for the virus. And as a result, the genetics of the virus will change to meet the challenges of that environment. So eventually what we see is distinct genetic profiles of HCV emerge. And this is where we get the differentiation of the 7 genotypes. So with different genetics come different amino acids, and thus proteins whose structure may vary slightly from one another. Different amino acids can have different chemical characteristics. And so oftentimes a structural change is also a chemical change. And this is very important because the new class of drugs I'm going to talk about work by recognizing both the structure and the chemical signatures of these viral proteins. And that new class of drug, as you know, are called direct-acting antivirals, or DAAs. And these drugs have been developed and improved substantially over the past decade. The viral proteins necessary for keeping the virus alive that I mentioned, well, these are often enzymes, which are just proteins that facilitate some chemical reaction. The molecules that these enzymes naturally work on are known as substrates. So to carry out a reaction, the enzyme must use what is known as its active site to attach to the substrate. So in the figure, the enzyme active site has a triangular shaped cavity, which is the gray figure. If you look at the substrate, you can see that it has a triangular portion that could easily fit into the active site. And so the basic way these drugs act is not particularly new. These are what are known as competitive inhibitors, which you probably could tell from the title of the diagram. So what these DAAs do is they compete with natural substrates to bind with the active site of a particular enzyme. And this prevents the substrate from binding, and therefore the enzyme cannot perform its function. The enzymatic proteins that these DAAs have been designed to target are proteins called protease and polymerase. And these are viral machinery that are critical for the viral life cycle, namely for viral replication. And so for this, I will focus on the viral protease as a target for DAAs. The major function of a viral protease, to get a little technical, is it cleaves large polyprotein precursors to yield functional products. And this process, all you really need to know is that it's necessary for replication. So before we get to specifically the protease DAAs, I want to point out that there are a bunch of different of these inhibitors which can be distinguished by their inhibitory targets, of which there are 3. So the targets are called NS5B, which is a viral polymerase, the NS5A, which actually doesn't have any enzymatic activity, but it is known that disrupting this protein serves to disrupt the HCV RNA replication for reasons that have not been fully elucidated in the literature. And then finally, there's the NS3/4A protease. And targeting this protease has gotten the most attention for the treatment of this disease because of how effective it is. And so I think it's important to point out for clinical use, often 2 of these direct-acting antivirals will be used in one treatment to attack different pathways to ensure the maximum efficacy in treatment. And so in order for these DAAs to successfully bind to the target active site, they must be able to conform to a particular shape and size that is able to fit into the enzyme's active site. Now, the inhibitor also has to have a chemical composition that is able to interact strongly with amino acids of the protease. And these inhibitors use various intermolecular forces to latch on to their target as best they can. Those forces are the electrostatic force, which is the attraction between opposite charges. There is hydrogen bonding, and so hydrogens on the inhibitor, on the drug, have a partially positive characteristic, and this partial positivity is able to hold on to any partially negative atom on the enzyme. So this is a sharing of a hydrogen atom that in bulk adds quite a bit of stability. There is also what are known as van der Waals forces, which are a type of transient electrostatic interaction. And finally, there's the hydrophobic or nonpolar groups will interact with each other. And this excludes water and allows for greater stability. Now here I have the chemical structure of 6 different protease inhibitors. And this is just to give you a sense of the size, the shape, and the chemical characteristics that these inhibitors are using. And so even though these target the same protein and are roughly the same size, they can vary slightly in their structure and chemical composition. And even the smallest of these variations can result in orders of magnitude increase or decrease in the drug's ability to bind to the active site and therefore its efficacy. And so for simplicity's sake, I think we should focus on just one, this one in the bottom right called glecaprevir. And so here, this drug has a lot of hydrogen bonding potential. So the nitrogens, oxygens, and fluorines, which are the N's, O's, and the F's, are all electronegative. And so they are able to share a hydrogen atom with other electronegative atoms on the viral protease, keeping the drug in place and preventing the substrate from binding. These nitrogens, oxygens, and fluorines can also form nice electrostatic interactions with the charged amino acids that may come off the protease. The hydrophobic portions, mainly the carbon-dense regions, are where they rest very nicely up against other hydrophobic portions of the protease and add stability. And then the heterocycle, which is the part of the structure that I have circled now, is responsible for van der Waals interactions with the protease, and this also keeps the drug stuck to the active site to prevent the substrate from binding. And so the scientific community studying these drugs can actually use techniques like X-ray crystallography to see exactly how the drug binds to the protease using these intermolecular forces. And so here is a crystal structure of that same DAA, glecaprevir, bound to the active site of the viral protease enzyme. And so the white cloud background is the enzyme active site. And the blue stick figure, the drug, is the inhibitor. And this rendering focuses on the hydrogen bonding between the two. The hydrogen bonds formed by the drug are shown by dashed lines, and the red dots you see are positions of water molecules coordinated around the drug. In the white protease, you can actually see faint stick figure shapes, and these are amino acids sticking off of the protease. Some of these amino acids are interacting with the drug via hydrogen bonding. So using this technique, specific amino acids that are sticking off the enzyme that these inhibitors interact with can be identified with precision. And if we remember that there are 7 different genotypes, this means that the active site of our viral enzyme can be slightly structurally and chemically different among these genotypes. And this has been a major obstacle to treatment because it is very difficult to make one drug that interacts well with all genotypes. Now, it is actually this very drug, glecaprevir, that is the first to essentially solve this problem. And so here I have a graph showing just how effective in comparison to previous DAAs glecaprevir is. This graph shows the Ki values, which is an inhibitory constant. And the smaller the Ki, the greater the binding ability and the greater ability the drug has to inhibit the enzyme. And the smaller amount of medication is needed in order to inhibit it. So glecaprevir, or GLE, is represented by the blue bars. The x-axis shows different genotypes. The lowercase letters are the subtype, and the y-axis shows Ki in concentration. And as you can see, effective inhibition using GLE requires orders of magnitude less drug than using alternatives. So it seems to have the particular chemical composition and structure to bind to the active site better than any of these other drugs. And it can do this for every single genotype. So this is a very accomplished drug in this regard. But one thing that this drug is not as accomplished in is its protection against HCV drug resistance. And so drug resistance arises from the same evolutionary mechanism that results in the emergence of different genotypes that we went over. The RNA virus can replicate very rapidly. There are billions of virions made daily. And in the replication process, the RNA, which is the genetic code, needs to be copied and exported for the virus to be made. This is not a perfect process. Errors can occur, and these errors result in the encoding for different amino acids in the protease. With different amino acids come different chemical properties, and so if one amino acid on the viral protease that is critical for drug binding is substituted with another, it could render the protease unable to interact with the drug, making the drug completely ineffective. And this type of substitution is called resistance-associated substitution. So just to give you the proper definition, it is defined as any amino acid change at a position that has been associated with reduced susceptibility of a virus to one or more antiviral drugs. And so as the virus is replicating and accruing these errors, it is exploring its own genetic territory in hopes of increasing its ability to survive. And so if someone is given a treatment regimen of a pair of these DAAs over, say, 12 weeks, and the virus is not eradicated, that is a whole 12 weeks where the virus is operating and replicating under selective pressures that ultimately produce a virus population better equipped to evade the drug, stay alive, transmit itself, and cause liver damage to more and more people. So with this drug, it seems that it works with all genotypes, and yet it's still susceptible to drug resistance. So why is this the case? Well, in order to kind of provide an explanation for these observations, I think we should take a look at the substrate envelope model. Now, this model was first conceptualized for HIV proteases and recently found to be applicable to hepatitis C, to HCV proteases. And so for a successful replication of HCV, the viral protease has to be able to bind to natural substrates. And typically those substrates, when bound to the active site of a protease, adopt a conserved consensus volume. And this is termed the substrate envelope. And so on the right, I have shown multiple natural substrates of HIV, and they are superimposed to reveal that there is a conserved region. That region is the substrate envelope, and that is shown by the blue highlighted portion. And so it turns out that inhibitors to HIV protease also have a conserved consensus volume when bound to the active site. And this is called the inhibitor envelope. So what we can do is we can take the inhibitor envelope and substrate envelope and superimpose them to see some differences. And so the inhibitor envelope, the red, superimposed onto the substrate envelope, the blue, you can see that it's protruding beyond the substrate envelope. And so what this means is that when the inhibitor is bound to the active site, it will make contact with extra protease amino acids that natural substrates do not. And it turns out that many of these amino acids correspond to previously known HIV resistance-associated substitutions. So this elucidates a little bit about drug resistance. Now, this observation is also seen in HCV, so hepatitis C proteases. And so the image that you see is of multiple protease substrates superimposed to reveal that there is a conserved region called the substrate envelope. Now, unfortunately, I don't have a visual of this, but if we were to superimpose HCV inhibitors onto this image, we would see that these protrude slightly from the substrate envelope. And as a result, we'll make contact with amino acids of HCV protease that correspond to resistance-associated substitutions. And a majority of these RASs are found on the region that don't interact with substrates, but do interact with inhibitors. And this makes sense from an evolutionary standpoint because changing an amino acid at a place that makes contact with a substrate may render the virus unable to bind to natural substrates, and this would be a self-defeating activity because the virus could no longer replicate. So these regions can't really change too much, or else the virus won't be able to survive. So regions of the protease that do interact with the substrate envelope are evolutionarily constrained in this way. There's not a lot of difference even across genotypes. From this understanding, it seems that the best strategy for drug design is to synthesize a drug that occupies space only within the substrate envelope, and this drug would interact with only regions of the enzyme active site that don't have the flexibility to adapt and become drug resistant. This not only would have the highest probability of avoiding drug resistance, but it would also increase the likelihood of the drug working across many different genotypes. So we had two observations we wanted explanations for. Glecaprevir works for all genotypes. When superimposed with the substrate envelope, it has very few protrusions. And so this means that it interacts primarily with highly conserved regions and is therefore able to bind to the protease of all HCV genotypes. Now, this drug is also susceptible to drug resistance, and the reason for this is that when superimposed onto the substrate envelope, glecaprevir does have a few protrusions. It extends beyond the substrate envelope. And this means that when bound to the viral protease active site, it makes contact with amino acids that have the potential to change for drug resistance without the virus losing its function. And so this is a 3D rendering of GLE in the active site of the protease of genotype 1. The coloration is showing the degree of conservation among genotypes, and the red coloring indicates highly conserved regions, whereas the green is variable or not conserved. So you can see there's a lot of red surrounding glecaprevir, and this is a good thing. The drug is using highly conserved regions among genotypes to inhibit the protease. And so in 2017, glecaprevir was FDA approved for HCV treatment, and this was approved in combination with an NS5A inhibitor called pibrentasvir, and both are taken daily over the course of 8 weeks. And thanks to glecaprevir, this treatment regimen effectively cures people of hepatitis C regardless of genotype. And so this is a figure taken right from a paper. The only thing we need to worry about here are the dark blue bars where it says SVR beneath it. And so this was a study done in Italy where a total of 723 patients, 50% males, 50% females, who had HCV were treated over an 8-week period with this combination of drugs. And nearly every single patient was cured. And they showed this using what are known as SVR rates. And this is called sustained virologic response. A successful sustained viral response means that there is no HCV virus detected in the blood for a certain amount of time after the completion of the treatment. And so the SVR, shown by the dark blue bars, you can see that at 8 weeks, there's a 99.2% SVR rate, and at 16 weeks, there is 100% SVR weeks. So none of the patients that underwent this treatment showed any HCV virus detected in their blood. So these are very effective. However, these turn out to be extremely expensive. They are among the most expensive oral medications in history. Wholesale acquisition price, which is the published or sticker price of medications set by pharmaceutical companies, range from $417 to $1,125 per day. And a 12-week course of sofosbuvir, which was the most effective DAA up until the discovery of glecaprevir, costs $84,000 for a standard 12-week treatment. Now, the cost of production is estimated to be much, much less than that. Pharmaceutical companies justify this significant discrepancy in the wholesale acquisition cost and production cost based on the need to recoup large expenses incurred during the research and development process of the medication. So patients don't actually pay $84,000 straight up. Luckily, medical insurers can negotiate price reductions through a third party, and this helps bring treatment within reach of some people. However, it is still exceptionally expensive. And if we remember, HCV disproportionately affects people from low-income regions. Paying even $26,000, which is the cheapest cost for one of these treatments, is nowhere near close to what it needs to be. And so a tremendous amount of progress has been made. Mavorite, the combination of glecaprevir and pibrentasvir, is the most effective treatment, which has a reduced span of 8 weeks instead of the typical 12. It is effective at curing people of HCV across all genotypes, and its development has led to insights into HCV drug resistance and pan-genotypic efficacy. But cost is a major problem. So there needs to be, the need remains for the scientific community to pursue new DAAs that are effective for all genotypes and that have reduced susceptibility to drug resistance. And it seems like the best strategy to design these robust DAAs is through the use of the substrate envelope model. And so with that, I would like to say thank you to Stefan for helping me with this literature review, to Deanna and Graham for running Chem 680, and to everyone in the chemistry and biochemistry realm at Lawrence who have shaped my experience over the past 4 years. Here I just have some references for my literature review, and at this time I can take any questions that you may have.
Yay! Any questions?
Connor, could you go back to the slide showing the 100% cure rate?
Yes.
So on this slide, what are the numbers at the bottom of the blue bars?
That is a good question. I am not entirely sure. When looking at these, or when looking at the exact paper, it didn't give a great description of the numbers at the bottom. You can see the absence of detectable hepatitis C virus, RNA 8, 12, 16. That was the extent of the description that they gave. But if I were to guess, the 80 over 80, if you see in the 12 to 16 week, would be potentially the number of patients, but that doesn't seem quite right because the numbers do vary. So unfortunately, I don't have a great answer for you.
It's definitely got to be the percentages that you see are just those products, right?
Right.
Because earlier you can see in the middle it's 450 over 600 is exactly 75%. So that's good.
Other questions?
So what is going to bend this cost curve down, right? Is this something that we're kind of locked into? Does this require, more drug development, or is this something that when it comes off patent, it's going to plummet? What do you think the prospects are?
Well, there are two strategies for that. You could try and reduce cost from the economic side or from the scientific side. And so the scientific community, to reduce the cost, would be to synthesize and get out as many of these DAAs that are effective as possible. And so one of the reasons why they are so expensive is because there's only a few of them that are really effective. And so just kind of flooding the market would be a way to reduce costs. But then you could approach it from the economic side, from policy side, which may be more effective. And if there is some sort of subsidizing of these drugs because of the recognition of the need for them, then pharmaceutical companies could reduce those costs. And there's been a lot of scrutiny over the such high cost for these treatments. It's kind of like having the cure for something on the top shelf and you're not tall enough to reach it and you don't have a ladder. So it's right there, but people aren't able to afford it. So there has been talk of reducing the cost just with subsidies for these companies that are producing them.
From what I understand, from a hospital level standpoint, even with the expense of the drug, it still saves money per patient in the long run because there's so much more, follow-on problems that will come up that you now don't have to worry about. So.
Yeah.
I'm going to ask a question. How would you consider this in terms of kind of global access? Are these being accessed equally globally, or are there preferences to more economically advantaged countries to be able to access to the DAAs in general?
Yes, these have been developed primarily in the United States, and especially because of the cost, they favor the economically advantaged. And so the access, just like the distribution of the disease, the access to treatment is also skewed, but it's skewed in the opposite direction. And so that's part of the problem, and that's why there's such a need to close that gap. So yes, we do see that as with most anything, the economic incentives are not allowing for the optimal solution for patients. And so the places like in China, Australia, Cambodia, the countries that I mentioned earlier, they are hit the hardest, and access to these DAAs is not quite what it is, say, in the United States. So that's also a gap that we need to close.
Other questions?
I have a question. So you talked about how we have like 7 different genotypes of this virus, and that's distributed differently around the world. Is this distribution due to like the different let's say different people around the world? So like, I don't know, like Caucasian people will be infected by these strands of the virus, and like East Asian people will be infected, because you would think like it would just spread around the world instead of having certain like genotypes allocated throughout the different parts of the globe.
Mm-hmm. Yeah, so the differentiation that emerges with these genotypes is is definitely a product of different environments. And I don't know, and that environment would be the immune system of that particular individual. And so if you have populations that may differ in their immune response, you're going to see viral populations that emerge with different mechanisms, different structures, different chemical compositions to meet the different challenges of those populations. And so it seems that, because there are different strains that affect, or different genotypes that affect regions more or less, it seems like there is a difference in that population that may have allowed for that specific genotype to arise. But I don't know if it maps specifically on with race, but I do know that with different environments, you're going to see different genotypes emerge. Did that answer your question?
Yes. Sorry for the dogs, by the way.
No worries.
Any other questions? Well, let's thank Connor for an excellent talk. And if you would like to stay afterwards and talk to Connor, great. If not, thank you for joining us. And I hope to see you again we have 3 more days of talks, Friday, Tuesday, and then Wednesday. 2 talks each of those days. So come join us for more.